This is the AP Physics B FRQ, and we have a ball of mass 0.5 kilogram initially at rest, and it's kicked directly towards the fence from a point 32 meters away, as shown above. The velocity of the ball as it leaves the kicker's foot is 20 meters per second, and it's at an angle of 37 degrees above the horizontal. The top of the fence is 2.5 meters high, and the ball doesn't hit anything while it's in flight, and air resistance is negligible. So the first thing that we want to do is set up a chart like I did in the top left corner, so we can separate our x and our y values to make sure that we don't get mixed up when we're doing equations. And then we can use a triangle like shown in the top right corner to be able to find our initial velocities of both the x and the y components. So to do this, we already know our hypotenuse because it's in the diagram. It's 20 meters per second, and we also already know the angle, which is 37 degrees. So we're going to use the sine and cos values to be able to find the initial velocities of both. So on this side, we multiply 20 times 0.6 to be able to get 12. And that is going to be our y initial velocity, and the bottom side we multiply 20 times the cos value of 37, which is 0.8. So 20 times 0.8 would get us 16 meters per second, and that is going to be our x initial velocity. So now we can go ahead and plug that into our chart. The first question asks us to determine the time it takes for the ball to reach the plane of the fence. So for this, I wanted to use the equation delta x is equal to v x initial times time plus 1/2 times x acceleration times t squared. So we know that delta x in this situation is going to be 32 meters because that's how far away the fence is from the kicker. And we can also already cross out the second part because since the acceleration is always going to be 0 for horizontal acceleration, that whole part is just going to go away. So we're left with delta x is equal to vx initial times time, and so we can plug the value that we just found for vx initial, which is 16. So we have 32 is equal to 16 times time, which gives us that time is 2 seconds. The second question asks, will the ball hit the fence, and if so, how far below the top of the fence will it hit, or if not, how far above the top of the fence will it pass? So for this question, I want to use the equation delta y is equal to vy initial times time plus 1/2 times y acceleration times t squared. It's actually the same equation that we used for the first problem, but in this one we're going to use the y components. So in this case, we need to find out how high up the ball is going to go at 2 seconds, and so we're going to solve for delta y. So we can just go ahead and plug in the values that we already know from our chart to be able to solve this. So it's going to be delta y is equal to 12 because that's our initial y velocity times 2 seconds plus 1/2 times -10 because that is the acceleration due to gravity times 4 because it's 2 squared. And we can simplify that to delta x is equal to 24 minus 20, and that gives us 4 meters. So the ball is going to be 1.5 meters above the fence because the fence is 2.5 meters tall, but the ball is going to go 4 meters into the air. Third question. What happens to the time spent in the air if the mass of the ball is doubled? So the time spent in the air if the mass of the ball is doubled is actually still going to be the same because we don't have mass in any of our equations, and unless doubling the mass would somehow change our launch angle or change our initial velocity, if that happened, then we would have a difference in the time, but since that isn't happening, it doesn't have any effect on the time. So we're on to the next set of questions. And so this one is asking, if the ball is kicked at an angle of 67 degrees instead, will the acceleration of the ball be greater than, less than, or equal to the acceleration that we just had? And it's going to be equal to, because horizontal acceleration is always going to be 0, and vertical acceleration will always be the same due to gravity. So just because the launch angle changes, that will not change the acceleration. And so this next question is going to ask us to graph both the horizontal and vertical components of velocity. So the first one is asking about horizontal, and we already know that we don't have any acceleration horizontal. And in a velocity versus time graph, the acceleration is shown through what the slope is. So we don't actually have a slope in this graph. It's 0 because it's a constant graph. So our equation is going to be v of x is equal to 16 meters per second. And it just stays at that point throughout the entirety because we have constant horizontal acceleration. And it stops at 2 seconds because that's the point where the ball passes the fence and is no longer going to be part of the graph. The second graph is asking us to graph the vertical component of velocity, and here our equation is going to be v of y is equal to negative 10 times t plus 12, where negative 10 is our slope and 12 is our y-intercept. In this case, negative 10 being the slope shows us what the acceleration is, because acceleration is shown through the slope of a velocity versus time graph. And the y-intercept in a velocity versus time graph is going to show us the initial velocity, which is, and we have that as 12 because that's what we calculated by using the triangles in our first step. So that's why it starts at 12 and then it has this slope of negative 10. And then on the axis you can see that there's a change in direction, and that's just as a result of the parabolic motion of the ball. The velocity is going to change from positive to negative. And this graph also stops at 2 seconds because that's when it's going to pass the plane of the fence. And that's all. Thank you for listening.